Point 1, random forests introduction. Bugging or bootstrap aggregation is technical for reducing the variance of an estimated prediction function. Bugging seems to work especially well for high variance, low base procedures such as trees. For regression, where simply feed the same regression through many times to boost the sampled versions of the training data and average the result. For classification, a commit of trees each cast a vote for the predicated class. Boosting in Chapter 10 was initially proposed as a commit method that although unlike begging, the commit of weak learns evolves over time and the member casts a weighted vote. Boosting appeared to dominate begging on most problems and became the preferred choice. Uh, Random forest is the substantial modification of begging that builds a large collection of decorrelated trees and then averages them. On many problems, the performance of random forest is very similar to boosting and they were simpler to train and tune. As a consequence, random forests are popular and implemented in a variety of packages. Point 2, definition of random forest. The central idea in begging is to average minimum noise but approximately unbased models. Hence reduce the variance. Trees are ideal candidate for begging science. They can capture complex interaction. Algorithm for uh, draw a bootstrap sample z of size n from the training data. It's grow a random forest 3t to the bootstrap date by repeating the following steps for each terminal node of the 3 until the minimum node size n is reached. Select M and pick the best variable and split the node into two data nodes. As the second term disappears but the first remains and hence the size of the correlation of pairs of bagger trees limited the benefits of averaging. Picture 1, bagging, random forest and gradient boosting applied to the spam date. For boosting, 5 node 3s were used. The number of trees were chosen by tenfold cross validation. Each step in the figure or picture 1 corrects point of change in a single misclassification. Not all estimators can be improved by shaking up the data like this, and it seems that high non-linear estimations such as trees benefit the most for bootstrapper trees. Is a typical small and while is not much larger than variance for the original tree. On the other hand, bagging does not change linear estimates such as the sample mean. The pairwise correlation between bootstrapped means is about 15%. Page 2, figure 2, the result of 50 simulation from the nested shapers model in ERL 10, the bias decision boundary, the surface of shear. Page 2 or figure show the test error progression on 2500 trees for the three methods. In the case there is some evidence that gradient boosting has started to overfit, although tenfold cross validation shows all 2500 trees. Figure 3 it's random forest compared to gradient boosting of the California housing date. The curves respect mean absolute error on the test date as a function of the number of trees in the models. Two random forests are shown with form static values and have interaction depth of 4 and x. The boosted models outperform random forest. Figure 4 OB. This is transcription. Error error computed on the spam training date compared to the test error computed on the test set. Random forest will scorn test on the mean deficient in absolute errors has an values. For large M, the random forest performed no better. Next point, details of random forest. We have glossed over the distinction between random forest for classification versus regression when used for classification, and the random forest obtains a class word from each three and then classification using majority word. Next point, out of back samples. An important feature of random forest to the use of out of back OB transcription samples. Next point, variable importance. Variable importance plots can be consumed for randoms forest in exactly the same way as were for gradient boosted models. And boosting ignores some variables completely, which the random forest doesn't note. The candidated split variable selection increase the chain that my single variable get include. And the decrease in accuracy as a result of this permuting is averaged over all threes, and the randomizing effective weight the effects for a variable. Figure 5, variable important plots for classification random forest ground on the spam date. The left plot by the important on the Gini splitting index as in gradient boosting. The rankings compare well with the ranking produced by gradient boosting. Figure 6, proximity plot for random forest classification ground to the mixture date. Next point, proximate plots. This is proximate plots for random forest, often looks very similar irrespective of the date, which casts doubled on their utility. And since the mixture date are two-dimensional, we can make point from the proximity plot of the original coordinates and get a better understanding of what they represent. Next point, random forest and our thinking. When the number of variables is large, but the fraction of relevant variables small, random forests are like to perform poorly with small m. Um, m, this is meaning, and at each split the change can be small that the relevant variables will be selected. Figure 7 show the result of a simulation that support this claim. This robustness robust robustness is large due to the relative and another claim is that random forest cannot overfit the date. Future figure 8 show the modest effect of depth control. A simple regression example classifies there's less sensitive to variance. uh, just figure 7, a comparison of random forest and gradient boosting on problems with increasing numbers of noise variables. In each case the true decision boundary depends on two variables and an increasing number of noise. Random forests use the default values at the top of each pairs in the probability that one of the relevant variables is choice at the any split. Next point, analysis of random forest. In this section we analyze the mechanism at play with the education randomized employed by random forest. For the discussion we focused on regression and square error laws since this gets at the main points. Next points, variance and the decorrelation effects. More more formal. Um, more formal, which present figure 8, the effect of tree size on the error in random forest regression. In this example, the true surface was additive in 2 of the 12 variables. Here more formals and next figure 9, number 9, correlation between pairs of trees drawn by a random forest regression algorithm as a function of m. The box plots represent the correlation at 600 randomly chosen predication point x. Next figure 10, simulation result. The left panel shows the average variance of a single random forest 3 as a function of within refers to the average within sample contribution to the variance result from the boosting, sampling and split variable sampling. Next point, bias is in the backing the bias of a random forest in the same as the bias of any of the individual sampled trees. These patterns suggest a symmetry with the right regression, and the right regression is useful when one has a large number of variables with similar sized coefficients reach shrinks there towards zero, and those of strongly correlated variables toward each other. Next point, adaptive nearness neighborhoods, neighbor, neighbors, соседи. Uh, the random forest classification has masters common with the continuous neighbors classification in fact weight whereas there were signs each trees grow to maximal size. Future figure 11 demonstration the symmetry between the decision boundary of three nearest neighbors and random forest of the mixed date. This figure 11 random forest version 3 on the mixed date. Bibliographic notes. Random forest description here were introduced by Bremen. Uh, it's all. um, mm, my opinion. Random forest is a powerful machine learning algorithm that is used in classification, regression, and other areas of data analysis. This method is based on the ensemble principle, combining many decision trees to make a more reliable and accurate decision. Here are some basis aspects and important points regarding random forest. Ensemble of decision trees, uh, reducing overlifting, emission resistance, processing large amounts of data, assessing the importance of futures, application in various tasks, and overall random forest is an important component of machine learning tools that brings stability, uh, robustness, and accuracy to a variety of data analysis problems. That's all.